Welcome. In this session, we'll continue our discussion of using the method of substitution to find indefinite integrals. One thing you should be aware of is that if you have exponentials or logarithmic functions, you might have to use rules of exponents or rules of logarithms to rewrite the function before you can integrate. Often, one form of writing the function makes it easy to find the antiderivative, whereas with other forms, it's a lot harder. In our first example, we have 1 plus e power 2x over e power 5x. If we follow my usual practice, set the denominator to be u, so u is e to the power 5x, then du will be e to the power 5x times 5 dx, and there is no e to the 5x in the numerator. Instead, I'm going to do what we did when we had a power in the denominator. Distribute the denominator over the two terms and rewrite each term using rules of exponents and negative exponents. 1 over e to the power negative 5x is e to the power negative 5x. E to the power 2x over e to the power 5x is e to the power 2x minus 5x. And 2x minus 5x is negative 3x. So I can rewrite the original integral as the integral of e to the power negative 5x plus e to the power negative 3x. Now I can integrate each of the terms using our general rule for exponentials. Integral of e to the power kx dx, if k is a constant, is e to the power kx over k plus the constant of integration. So for e to the power negative 5x, an antiderivative is e to the power negative 5x over negative 5, and for e to the power negative 3x, an antiderivative e to the power negative 3x over negative 3, and for the general antiderivative I need the constant of integration. We can rewrite this a little bit by putting the negatives in front instead of the denominator. You can also write the negative exponents using fractions instead, but I will stick with my usual practice of leaving negative exponents as they are, unless I'm going to do more algebra. Our next example is similar. It looks a bit different because there is a square root in the denominator, but again I have a single exponential inside the square root, so I can write this using fractional exponents. Square root is same as power 1/2, so I have e to the power x squared plus 2, the whole of that to the power 1/2, and by the rules of exponents I can just multiply the exponents together. So I get e to the power 1/2 times x squared plus 2, and if I use the substitution u equals 1/2 x squared plus 2, du will be 1/2 times 2x dx, or x dx. I have that in the numerator. So now I can rewrite the original integral using this substitution. The denominator is e to the u, the numerator is du. Again, you want to bring the exponential in the denominator to the numerator, so we can apply our rules. I have integral of e to the negative u du. Exponent is negative 1 times u, number times the variable of integration. Since the base is c and antiderivative is just the exponential over the coefficient of the variable in the exponent. So e to the negative u over negative 1, and then I have plus the constant of integration. I must now go back to the original variable, because 1 over negative 1 is just negative 1. E to the negative u is e to the power negative 1/2 x squared plus 2. That gives me the answer to the original integral. This concludes our two examples with exponentials. Next time we will look at an example involving logarithms.